Okay, so we're going to continue our conversation about the bone growth, and then we're going to talk about the remodeling, and then we're going to talk about some problems and pathologies associated with the bone development. And the first thing to talk about is the hormones that regulate the bone. We didn't talk about endocrine system, but we kind of mentioned that hormones are the compounds secreted specifically, sorry about that, specifically into the blood, okay? And there are multiple hormones that participate directly or indirectly in bone development. First and foremost, of course, is the growth hormone. Growth hormone, not surprisingly, stimulates growth, and in relation to bone, it increases the mitotic rates for osteoblasts and increases the production of osteoid. So essentially, the lack of growth hormone stunts the bone growth and leads to the condition you may have heard about. It's called dwarfism, pituitary dwarfism. Growth hormone is not produced, people do not grow, their bones do not elongate because cells do not divide. On the opposite end, the overproduction of growth hormone leads to the abnormal growth, okay? What is called gigantism. And in the adults, in the adults, whether the excess of growth hormone is genetic or due to the abuse of growth hormone as potential performance enhancement drug, the condition associated with its excess is called acromegaly. In acromegaly, one of the features of people who suffer from that condition are enlarged bones of the face, especially mandible, hands and feet. They have very characteristic facial appearance and large hands and feet. Thyroid hormone increases the rate of the protein synthesis. Obviously, it assists the growth hormone, in a sense, to in production of osteoid. Anything that increases protein synthesis will increase the rate of the bone growth. One of the extremely important hormones for the bone growth are androgens, testosterone and estrogen. Testosterone and estrogen have three critical functions in terms of the bone growth. First, they are responsible for the adolescent growth spurt. Initially, they stimulate the anabolic hormones, so they stimulate the protein synthesis and division of osteoblasts in the long bones. So that growth, when you start to grow like 3-4 inches over the summer, that's because you start to produce testosterone if you're a male or estrogen if you're a female. But eventually, that production of testosterone and estrogen will lead to the closure of the epiphyseal line. The stabilization, the peak levels of testosterone and estrogen will close the epiphyseal line and will cease the growth. And then, after a while, in females, production of estrogen rapidly declines after the menopause. That decline in estrogen production is associated with a condition known as osteoporosis. Because estrogen and testosterone, they both contribute to the retention of calcium in the bone. When testosterone and estrogen are at the high levels, calcium is in the bone. When they decline, bone starts to get resorbed, calcium leaves the bone, it's not there anymore. And since in males, testosterone levels, they remain steady for a longer period than estrogen levels in females. Does that make sense? Other hormones that are quite important. Insulin, well, we'll put insulin in the category, it provides energy. That makes sense. If there is no insulin, there is no glucose uptake from the blood, there is not enough carbohydrates in the cells cannot grow. It has sort of an indirect role. Calcitonin, if the blood calcium is high, and calcitonin will decrease the resorption of the bones and will actually promote the deposition of calcium into the bone. And finally, parathyroid hormone, or PTH, produced by parathyroid glands. We can't really see them, but let me give you sort of a heads up. So if you would look at this gentleman, this structure right here, the orange structure, is the thyroid gland. On the posterior surface of the thyroid gland, there are usually 4 tiny, well, not very tiny, noticeable, parathyroid glands that produce this hormone, PTH. The main function of parathyroid hormone in relation to the bone is to stimulate bone resorption. Not just for kicks, not just for resorption itself, but to promote, to maintain normal calcium levels in the blood. Does that make sense? Because bone is the main storage for calcium. You good? Go ahead.
People with kidney failure, the blood vessels can they get filled with calcium, and solidify?
Okay, so in people with kidney failure, hypercalcemia, elevated levels of calcium, will manifest mostly as the kidney stones. Calcification of the, you're not going to get really calcium in the blood vessels. When we refer to calcification, it means that blood vessels become less elastic. Does that make sense? We'll talk about hypercalcemia, hypocalcemia, and what are the outcomes of those conditions. Now, going back to the remodeling and oppositional growth. I mentioned before that oppositional growth is when bone becomes thicker. It grows in width, right? So what happens essentially, osteoblasts at the face between periosteum and the compact bone, they produce bone matrix, and that bone matrix is laid on the periosteal surface. Does it make sense? So that's what makes the bone thicker. You can see here added bone matrix. Okay? Now, osteoclasts on the endosteal surface, right here, that's endosteal surface. Osteoclasts will remove the bone on the endosteal surface. Does that make sense? So again, think about the bone like walls moving to the outside very slowly. Now, deposition occurs normally faster than breakdown. So what you end up with a bone that is wider, just the whole bone is wider, and the walls of the bone are thicker. The walls of diaphysis are thicker. Does that make sense? Okay? So it makes the bone strong, but at the same time, the bone isn't very heavy. Does that make sense? Good. Now, why do you grow? Can you consciously control your growth? Can you do anything about it? Not really. You can take growth hormone, yeah. You can stop eating, yeah. Or, just stop eating calcium and stuff like that. Yeah, you can. But What I'm trying to say is you just grow up, right? You just grow, okay? Your growth doesn't respond, it does respond to some cues, but let's put it this way. So if everything is abundant, okay, you will just keep growing. Now, the remodeling, the oppositional growth, the remodeling of the bone, provides the bone with a mechanism to respond to mostly mechanical stress. That makes sense. The mechanical demands, because that's what bones do. Okay? You can see it in many instances. For instance, if somebody has certain handedness, okay, like right-handed or left-handed, the hand that is used the most for mechanical tasks will have thicker bones because it experiences more significant stress. Okay, bone is curved. The highest thickness is at the place where the bone is, according to the forces that bend it, more likely to buckle. Okay? Trusses along the stress lines also is characteristic of, respond to the mechanical impact. Active muscles, large active muscles where they attach to the bone, you have projections. Does it make sense? All of it tells you that the bones respond to the mechanical stimulus. When people become bedridden, their bones, or they stay bedridden for a long time, the bones become featureless. Projections, tubercles, tuberosities are gone because there is essentially no mechanical stress applied to the bones. Go ahead.
So if there's already features before you're bedridden, would those appear?
Probably will be gone, yes. Because think about this. You may not notice it, but every time you walk, run, bend forward, sideways, lift something, muscles, many muscles in your body work. They pull on your bone. And we're not talking like doing the maximum effort, but it's a constant mechanical effort that remodels the bone. That make sense? Now, going back to James' question. Bone is constantly recycled. Okay? Spongy bone is replaced every 3 to 4 years. And the compact bone every 10 years. Again, as I mentioned, it doesn't mean that, it happens overnight. It's just, if you will sort of set certain time frame, and in 10 years, all bone that you had at this moment will be gone. Compact bone. Okay? Why it happens? The older the bone, the more brittle it is. So we need to constantly recycle. And that constant recycle maintains the bone shape, bone structure, normal. Does that make sense? The older the bone, the more brittle it is, the easier it is to fracture the bone. Does it make sense? Now, remodeling is a wonderful illustration right here. It involves two processes: the bone deposition and the bone resorption. Okay? You can see this red cells are osteoclasts, and these blue cells are osteoblasts. Osteoblasts deposit the new bone. Osteoclasts remove the old one. These combinations of osteoblasts and osteoclasts are called remodeling units. So the osteoblasts deposit the new matrix, new, unsolidified, soft matrix, which consists of the ground substance and the collagen fibers. And you can see as they deposit matrix. They form what is called osteoid seam. Between the osteoid seam and the mineralized bone, you can see that transition zone. Okay? That transition zone is called calcification front. Again, osteoblasts produce the matrix, which gets calcified and becomes an actual bone matrix. All right? Now, what triggers that calcification of the unmineralized bone is not known. Potential mechanisms, probably mechanical, and chemical signals. Okay? Very likely, the concentration of calcium and phosphate ions in the medullary cavity will stimulate the higher concentrations will stimulate the calcification of the unmineralized matrix. Matrix contains a bunch of glycoproteins and proteoglycans as well as collagen. Those glycoproteins and proteoglycans in the osteoid have a property binding calcium. Does that make sense? So you have osteoid, which contains both collagen and a lot of calcium binding proteins. If concentrations of calcium and phosphate are sufficient, then calcium and phosphate will be bound by those proteins in matrix, forming hydroxyapatite, mineralizing the osteoid. Does that make sense? Now, first of all, remodeling goes all the time. What regulates remodeling? Well, first of all, genetics. You know how they say some people have heavy bones, some people have lighter bones. Right? That's entirely genetic. Okay? You can look at people who, I always give that idea. It's not only about the scale, it's also about muscles, but does anyone more or less, like generally, follow marathons in the United States? Okay, which nations win marathons? Kenyan and Ethiopian. Okay, how do they look like those guys? Tall, lanky, skinny. Are you aware of any Ethiopian or Kenyan strongmen? Absolutely not. Northern Europe, Baltic states, Eastern Europe, Western Europe, Russia. Okay? How do those guys look? Yep, like bears, right? And their bones are huge, partially because of the exercise, we'll talk about it, but also it's just genetically. Okay? It's the genetic predisposition to a certain body type. Does that make sense? So, this is the genetic component. But along with that, there are two feedback loops, two regulatory mechanisms that will actually determine what your bones are going to look like. It's the calcium homeostasis and response to mechanical and gravitational forces. In terms of the calcium homeostasis, what do we need calcium for? Forget about the bones. Well, don't forget about the bones, but generally, what do we need calcium for? Say again?
Neurotransmitters.
So, release neurotransmitters, very good. What else? Bones, right? So we need bones and for signal transmission. It's also very important just the signaling ion inside of the cell and blah, blah, blah. But signaling and bones. What comes first? Signaling. Bone integrity is second. If organism has to sacrifice one, that one will be the bones. Does it make sense? So bones are always to be sacrificed. Now, how are they sacrificed? That's the responsibility of osteoclast. So this is the osteoclast. And now, to give you a little bit of a relaxation, sort of, I'm not going to ask about the chemistry of acid production by osteoclasts in the exam. Just want you to focus for a second, because this mechanism will come back in AP2. And if you don't want this mechanism to come back and bite you in the ass, you may want just to listen to it now. What happens in osteoclast? Osteoclast absorbs carbon dioxide. We have plenty of carbon dioxide in the body, is that right? Carbon dioxide inside of the osteoclast combines and forms the compound that is called carbonic acid. Carbonic acid then dissociates into the proton and bicarbonate ion. Bicarbonate ion is actively transported out of the cell via the chloride bicarbonate exchanger. Chloride gets into the cell, okay, and then is pumped together with hydrogen out of the osteoclast into so-called resorption bay. Does that make sense? Now, before we move on, this chemical mechanism, absorption of carbon dioxide and water form acid, which dissociates to proton and bicarbonate. This mechanism will be involved, just from the top of my head, digestive, cardiovascular, and renal. Okay? Now, what's going to happen to the bone if you pour acid on it? It will dissolve, right? That makes sense? Now, which component of the bone will actually dissolve as the result of acid action? So we have the bone matrix, okay, which consists of collagen, ground substance, and hydroxyapatite. Which part will dissolve? Sorry. No, hydroxyapatite. Salt, like calcium salt, it will become probably this, and water, I'm too lazy to equilibrate it, but the point is, you're going to get soluble calcium phosphate and water. Does that make sense? What about proteins? What can kill them? Lysosomes. From your previous biology courses, probably know that lysosomes, their function is to destroy whatever gets into the cell. If you release the content of the lysosomes out of the cell, this content, represented by various proteolytic enzymes, will break down proteins and whatever organic molecules you have. Essentially, what osteoclasts do at this resorption bay, they destroy the bone, they make calcium that's in the bone soluble, they destroy the protein component, and they do it for two major reasons. One, destruction of the old matrix and old osteocytes, and just dissolution of the old bone. And since they descend from phagocytes, they can phagocytose as well. Reason number two is to get the calcium in the system. So that calcium that's produced here, okay, will be released into the extracellular fluid and eventually will make its way into the blood. Does that make sense? Okay, so they clean up the bone, and they also, if calcium is needed in the blood, they also deliver calcium from the bone to the blood. Now, what is regulating the activity of osteoclasts? Answer is very simple. It's parathyroid hormone. This is how it works. When the concentration of calcium in your blood falls, and the interesting thing, it has to decrease in a very marginal level. As soon as the calcium in the blood goes down, the decrease in calcium is sensed by the parathyroid gland right here, well, right there in the back. In response to that decrease, chief cells in the parathyroid gland start to produce. You don't have to know about the chief cells, no worries, that's endocrine system. But I want you to know about parathyroid hormone, what happens. So parathyroid gland starts to produce parathyroid hormone. Parathyroid hormone stimulates the activity of osteoclasts. Osteoclasts resorb the bone. That resorption delivers calcium into the blood. It's all good. Does that make sense? Now, what type of regulation is that? Feedback. Yeah, negative feedback that results in the maintenance of homeostasis. You have a change, drop in calcium levels. You have a response, bone resorption. And you have calcium levels back to normal. That's the alleviation of the change. Does that make sense? Calcium, function, transmission of nerve impulses, muscle contraction, skeletal muscle contraction is, calcium is critical, smooth muscle contraction, cardiac muscle contraction. Blood coagulation, it's one of the coagulation factors. Regulates glandular secretion, critical for the cell division. So you can imagine that calcium is extremely important. So in the body, we have 12 to 1400 grams of calcium. If you prefer imperial system, think about 3 pounds. Okay? This is one of the most important things, tightly regulated. When I say tightly, it means that calcium concentration in the blood falls in a very narrow range. What is not tightly regulated? Say your blood glucose. Okay? It can fall to say 80 and you still feel fine. You can eat a chocolate cake. It can rise up to, I don't know, 400 or 500 and you're going to be okay. If you have functional pancreas at normal insulin levels, then you should be fine. Does that make sense? So it's pretty wide range. Calcium levels regulated very tight. So if calcium levels in the blood drop, PTH immediately removes calcium from the bones. Okay? Other responses that parathyroid hormone stimulates to increase the calcium levels, increased absorption of calcium from the intestine. For this, you need vitamin D. Okay? And decreased excretion of calcium in the urine. Does it make sense? Now, of course, intestinal absorption can go up only if you eat calcium. If you decide to completely abstain of any food that contains calcium, increased absorption doesn't really help if you don't have anything to absorb. That make sense? Now, this example gives me an opportunity to provide you with another idea. We're going to talk a lot about, how we elevate certain levels, how we elevate calcium, sodium, potassium, and whatnot. Okay? You have to appreciate one very important thing. How can you increase the level of a chemical in the body? There are 2 ways. Very general. So how can you increase the level of a certain chemical in the organism? So throw out less or take in more. Two ways. You have always, remember those. You have to think, okay, we need to elevate calcium. We can either eat more or absorb more, or we can pee out less calcium. Does that make sense? Good? Now, why it is so important? Because alterations to calcium levels result in the massive changes to neuromuscular activities. Hypocalcemia is generally associated with the hyperexcitability of the muscles. Not necessarily the strength, but excitability. Does that make sense? So low levels of calcium can be manifested by seizures and spasms. Okay. Nervous symptoms like irritability, hyperactive nervous system. One of the very characteristic symptoms of hypocalcemia are muscle cramps. There's also something that is called hypocalcemic green. One of the symptoms of sustained low calcium levels in the blood is the spasm on one side of the face, which makes a person like this. Okay? That's very characteristic. On the opposite, elevated calcium levels depress the activity of the nervous system, leading to the sleepiness, depression, various types of arrhythmias in the heart, and weakness of the muscle. Does that make sense? Another symptom of high calcium in the blood, if you have hypercalcemia, sustained hypercalcemia, your renal system, your kidneys will try to get rid of calcium by filtering it out. But if calcium concentration in the filtrate will be high, calcium will start to precipitate in the filtrate. And it will precipitate not in your urinary bladder, but it will precipitate in the renal pelvis. Forming inside of the kidney, it's going to form renal calculi or kidney stones. Okay? That's very common condition associated with hypercalcemia. Does that make sense? Now, we talked about parathyroid hormone. And parathyroid hormone increases the levels of calcium in the blood. Calcitonin is pretty much an opposite. Calcitonin works this way if calcium levels in the blood are high. What do you want to do with those levels? Decrease them. So calcitonin is produced. It's produced by not parathyroid but thyroid gland, and calcitonin leads to calcium deposition in the bone, and that deposition leads to decreased calcium levels. Are we clear with this? Moving on. What else? You haven't learned this yet, but I have my favorite hormone. It's leptin. I love leptin. Leptin is why I love leptin. Leptin is the only hormone which action we can consciously counteract. Let me explain. Growth hormone, what does it promote? Growth. So can you tell yourself, make a mental effort and say, I'm not going to grow. Although I produce growth hormone, I'm not going to grow. You can't. Okay? Testosterone in puberty. What does it promote? Except for the sexual behavior. Growth. Let's not talk about conscious effort to limit your sexual cravings, but can you stop growing? No, you can't. Insulin, what does it do? Reduces blood sugar, but stimulating uptake of carbohydrates into the cells. Can you consciously say nope? Nope, insulin is produced, but glucose is not going anywhere. I'm going to keep it in the blood. No, you can't. Leptin. You can overcome the effects of leptin, at least one. Leptin is the hormone of satiety. It signals that you had enough. When you eat, leptin gets produced and tells via hypothalamus, it tells your brain that you are full. Does that make sense? Now, I don't want to do like a poll here in the class, but admit to yourself, there are moments in your life when you have a cake and you had a piece of cake and or whatever you like, pizza, I don't know, and you realize that's enough. But then look, who can refuse another slice of pizza or another, and then another, and then another? You know that you stuffed, but you keep eating. I believe it happened to everybody at least once in their lives. Okay? Your leptin tells you, dude, you're stuffed, but you just keep eating. You consciously overcome, not because you want to eat, because it tastes so good. Okay? That's why I love leptin. And if you get rid of leptin gene, in mice, they become like spherical almost. In humans, they become really, really obese. Okay? That's genetic disorder. Now, leptin, the role of leptin in the bone regulation is controversial. Okay? Some studies suggest that leptin, by acting on the hypothalamus and producing Y2R compound, okay, inhibits the bone formation and therefore bone mass. So it inhibits osteoblasts and even stimulates osteoclasts, stimulates remodeling. However, in other papers, leptin is suggested to inhibit osteoclasts and stimulate osteoblasts. That makes sense. So the studies on leptin are quite controversial. But you have to appreciate this. Those studies are done in animals. Animals are very different from humans. They model. So you can't directly translate those studies. Now, another hormone that is implicated in the control of the bone mass is serotonin. Okay, now with serotonin we're more sure. So serotonin, it acts upon the hypothalamus, and hypothalamus produces chemicals that activate beta-2 adrenergic receptors, which then decrease the activity of osteoblasts. Does that make sense? So serotonin, by decreasing the activity of osteoblasts, will decrease the deposition of the new bone and therefore will lead to the lower density of the bone. Now, you may say, oh crap, especially with that controversial data about leptin, what am I supposed to know? Here's my answer. You have to understand the effects of a hormone, not the hormone, a hormone. So if I tell you, we have hypothetical hormone that stimulates osteoblasts, what will it result in? Higher bone density, lower bone density, higher bone resorption, lower bone resorption. Does that make sense? We have a hormone that stimulates osteoclasts. What does it result with? Due to the bone resorption. Yes, the bone resorption. Does that make sense? You have to understand that sequence of events. It's pretty much a question about the function of osteoblasts versus osteoclasts. And not specifically the hormone. Yes. That makes sense? Great. I hope I have an answer.
All about leptin.
Yes.
Is there a possibility then, like for people you say that have like the genetic factor of like
Not having leptin?
Can you like put that into people's bodies so they like don't eat that much?
They can have a supplement.
Yeah.
They can treat, yeah. They can give leptin as a drug.
Okay.
Of course, genetic intervention would be better, and I have an illustration in my endocrine lecture which shows the kid that had leptin deficiency at I think 4 years of age, and it's sad, it's horrible. The kid is absolutely morbidly obese, and then after a year of leptin therapy, he's absolutely normal, like not skinny but absolutely normally built. Okay. I'm telling you, leptin deficient mice, regular mouse weighs about 25 grams. Leptin deficient weighs 60 grams. And they can barely move because limbs barely touch the ground. They have such a huge bellies, they pretty much like crawl, they can't walk. Anyway, response to mechanical stress. So bones respond to mechanical stress. And the inner side, if you have a pressure here, okay, then the inner side of the bone will experience compression. The outer side will experience tension. Does that make sense? Those forces that act on the bone are going to be largest in the middle of the bone here, in the diaphysis. So it may not look like the bone is thickest here, but the walls are thickest. So medullary cavity is really thin in the center. Does that make sense? Okay? So what actually, in case of mechanical stressor, what type of signal regulates the bone remodeling? The short answer, we don't know. Presumably, electrical signals. We know that bones produce electrical signals when they are mechanically stressed. Those electrical signals direct the fluid flow between the osteocytes. The fluid goes through the canaliculi from osteocyte to osteocyte, essentially transmitting the signal on where the bone is supposed to be remodeled. Now, harkens back to what we talked about, the regulation, the bone remodeling. Integrity can be sacrificed. Bone integrity can be sacrificed if the person needs calcium, right? So we have two main contributors: mechanical stresses and mineral homeostasis. Does that make sense? So bones will be solid and will remodel and will adapt to mechanical stress only if you consume enough calcium. Only if calcium levels in the blood are sufficient. If you do not intake enough calcium, or there's a problem with parathyroid hormone, something like that, okay, then bones will not be solid. Okay? Am I clear? I want you to very clearly understand that the integrity of the bone is secondary to the calcium levels in the blood. And you can put all mechanical stress you want, but if calcium metabolism is impaired, the bone will be fragile and brittle. That brings us to the point of fractures. There's so many of them. Classifications, there's a huge whole bunch of classification of fractures. Okay? When we're young, it's usually due to some sort of a trauma. I know a lot of stupid stories about getting a fracture. In the old age, often it's the result of the osteoporosis, the thinning of the bone. Okay? One of the classifications, I wouldn't say most widely used, but it kind of makes sense, based on the appearance of the fracture. So fracture can be non-displaced or displaced. Bone ends keep normal position in non-displaced fracture and get out of alignment in the displaced. Does that make sense? Good? The fracture can be complete or incomplete. So, for instance, this is the green stick fracture, which is very common in children. Okay? When you break the fresh branch of a tree, it's often hard to break it completely. Same happens with the bones in kids. Because bones are not solidified yet, fractures are often incomplete. They don't go through the entire width or thickness of the bone. That makes sense?
What's technically better as far as repair goes?
Complete versus incomplete?
Yes.
Think about this. You can have, well, incomplete fracture is never displaced. You don't twist it. But say you may have complete non-displaced fracture, and it's fine. It will, like stress fracture, when ends do not even separate, it will heal in a month. Okay? Open and closed. I will never show you the picture of the open fracture. If you want, find it yourself. It's very unpleasant. Open fracture is the fracture in which bone penetrates the skin. Open fracture always requires surgical intervention. Okay? Open fracture is also called compound. Now, there are many other fractures, many other classifications. For instance, spiral fracture. Okay? When the fracture line is spiral. Epiphyseal fracture, bless you, when epiphysis separates from diaphysis. Epiphyseal plate fracture, I know it myself, I broke my son's hand once, it was epiphyseal fracture. We were playing soccer. It's when the fracture line crosses the epiphyseal plate, it heals pretty fast. Comminuted structure or comminuted fracture or compression fracture. It's very common in elderly, especially in the vertebrae. Vertebrae are brittle, and due to the stress, bones become crushed. Does that make sense? Now, fractures are treated by reduction, which means they are immobilized. If the fracture is displaced, ends have to be realigned. Realignment can be closed when there is a manipulation of the broken limb to put the bones together. So they put together, the person takes an x-ray, you look at the position, you realign them better. Okay? And especially in case of the compound open fractures, it's a surgical manipulation in which surgeon inserts wires or pins to secure the ends. It is often used in elderly who suffer from the neck fracture in the femur, which is very common. The head of the femur and the body of the femur are attached to each other by the pins or wires. Okay? That makes sense? Fracture has to be immobilized to accelerate healing. The length of the healing depends on how bad the break is. The age of the patient is very important. In elderly, fractures heal much slower. Now, how are the fractures, how do they recover? Okay. When bone is broken, blood vessels, of course, are disrupted. The blood flows into the fracture site, forming hematoma. So that's the first stage of the fracture. The site of the fracture is swollen and inflamed. Next, capillaries start to grow into the hematoma, bring phagocytes with them. Phagocytes clear the debris. Fibroblasts from the connective tissue, from the periosteum, starts to produce collagen fibers. This blue color is the new connective tissue matrix. Okay? Collagen fibers bring broken ends together. Fibroblasts, connective tissue cells, cartilage, chondrocytes, and osteoblasts, derived from osteogenic cells, will start to reconstruct the bone. They create what is called fibrocartilaginous callus. Okay, you can see this blue structure consists of the connective tissue and the cartilage. Okay? Does that make sense? So initially, the callus between the broken bones is fibrocartilaginous. It's a mixture of connective tissue, proper, and the hyaline cartilage. And then, osteoblasts and osteoclasts start to remodel this fibrocartilaginous callus into the bony callus. So spongy bone fills up the span between the broken ends. Does that make sense? Eventually, osteoclasts and osteoblasts, the remodeling units, will replace the spongy bone on the outer surface of the broken bone into the compact. Okay? Compact bone is laid down in exactly the same place that it used to be, and the final structure of the bone that is repaired will be the same as the structure of the original one. The reason for that? Same mechanical stressors. Think about this. When somebody breaks the arm, the cast is removed. You use the arm in exactly the same fashion. You play basketball, you carry bags, you do things that you regularly do with your arms. So the new bone that is laid between the broken ends experiences exactly the same kind of mechanical stress. And the bone develops the same way. Does it make sense? Pathologies of the bone. Lack of calcium mostly. Osteomalacia is the lack of bone mineralization, usually to the insufficient calcium in the diet. Osteomalacia is the word that is used for this condition in adults. In kids, osteomalacia is called rickets. Okay? And rickets in children appears as bone deformities of different sorts, most often bowed legs. Some physicians suggest that at a certain period of postnatal growth, all children go through the period of rickets. The severity of condition depends entirely on the supply of calcium in the diet, because the bone growth rate cannot be matched by the calcium supply. Does it make sense? When the bones become ossified, okay, when the skeleton becomes ossified, just cannot provide that much calcium. But severe rickets comes from the deficiency of vitamin D or insufficient dietary calcium. Vitamin D is produced mainly by your skin in response to UV light. So if you are exposed to the sun, it's not a problem. Back home, when I was a child, I'm not kidding, when I was a child, our winters are long and you don't spend too much time outside catching that winter sun. So what they were doing in child care centers, they had a UV lamp. And kids at the age of like 3, 4 had to undress to their undies. And I have the photograph somewhere. So it's a gigantic lamp. Kids, 4-year-olds, make a circle. And of course, they have to wear shades. So they all look incredibly cool, standing in the underpants and shades, and they being irradiated with UV to increase the vitamin D production in the skin. Okay. The most talked about condition associated with a bone abnormalities is osteoporosis. It's the group of diseases where the resorption of the bone happens faster than the bone deposition. There are plenty of risk factors, but let me put it this way. Petite Caucasian women after the menopause, period. So it's rates of it are much higher in the smaller women with smaller stature, women of Caucasian descent, women and men, because after the menopause, estrogen levels decline. Does that make sense? About 70% of women by the age of 80 experience osteoporosis. Okay? Estrogen declines, calcium deposition in the bone decreases. Men who undergo therapy for prostate cancer, androgen suppressing therapy, are also at risk because androgens keep your bones strong. If you suppress androgens, calcium is not deposited, right? And your bones become brittle. Does that make sense? What else? Smoking, low dietary calcium, low dietary protein, and insufficient exercise. And we'll talk about the treatments for osteoporosis in a second. Does that make sense? Now, osteoporosis is when resorption outpaces deposition. Paget's disease is sort of an opposite. Deposition is really, really fast. Deposition is quick, but it's messy and haphazard. And resorption is pretty much haphazard remodeling of the cell, of the bone. So it's poorly made bones, a lot of spongy bone. And that creates very particular appearances of people. Usually the skull is protruding forward very much. Okay, and legs about. We don't know the cause of the Paget's disease. It usually develops later in life, at the age of 40. It's probably somewhat genetic. Okay, but it's much less frequent than osteoporosis. Now, this is a very interesting table I wanted to pay your attention to. So that's the comparison of hip fractures in a certain population in North America and Europe. So I'm not going to go through all the numbers, okay? But let's take a glance at the age group which is the highest risk. Men and women older than 65 years of age. So 87,000 hip fractures in the 14,000 group. Okay? 20,000 hip fractures in 230,000 hip fractures in 20,000 group. So first of all, obviously females are at much higher risk than males. Can you see that ratio? Okay? So pretty much here it's what? 6 fractures per male, 11 fractures per female. Does that make sense? Look at Europe. I'm going to give you 3 fractures per male. Kind of 7 fractures per female. Although females in Europe are still at the high risk, the frequency of fractures in Europe is less than in the United States. Why? What is the difference in lifestyle between Europe and the US? Say again?
One thing that I noticed was there's a lot of people who ride bikes and walk.
Moving. Nobody drives, it's too expensive. Well, not nobody, but much less people drive. Here, come on. When I saw the drive-through liquor store, you gotta be kidding me. Okay. Now, here's everything drive-through. You can live in your car. Okay. In Europe, car is inconvenient and people move. And that tells you importance of exercise to prevent osteoporosis. And actually, exercise is one single best prevention method for osteoporosis. By exercising, what happens to your bones when you exercise? They become thicker. You building a savings account for when you are old. Does that make sense? You accumulate more bones so you have something to lose when osteoporosis hits you. Okay? Calcium, vitamin D, of course, but we take a lot of calcium and vitamin D as well. Hormone replacement, so using estrogen supplements. Quite controversial because estrogen supplements may lead to the increased risk of heart attack, stroke, and breast cancer, which is horrible, right? Drugs called biphosphonates, they inhibit the activity of osteoclasts by leading them to apoptosis, so they decrease the bone resorption and can improve the bone conditions, especially in the spine, which is susceptible to those comminuted fractures, to crushing fractures. Agonists of estrogen receptors, okay, being tested now, so they will stimulate estrogen receptors without stimulating estrogen susceptible cells in the uterus and breast, therefore decreasing the risk for breast and uterine cancer. Denosumab, the antibody against RUNC-L. Briefly, denosumab inhibits the osteoclast formation. Okay, but as always, prevention is better than treatment. By prevention, it means exercise. Exercise, weight-bearing exercise, resistance training. Calcium and vitamin D rich diet. No smoking. No alcohol. No carbonated drinks, because alcohol and carbonated drinks decrease the pH of the blood, and acidification of the blood is compensated by removal of calcium from the bone. Go ahead.
I have a silly question. But,
No.
If there's an older woman who constantly drinks sparkling waters, is that really bad for her then?
Not good.
Yeah.
Not good. Yes. Carbonated drinks should be excluded. Okay? Go ahead.
Like really far left. People who are getting the gender therapy, like what you call it, the gender alteration or whatever. Aren't they getting like
Estrogen?
and everything like that? So they're going to be at much higher risk for stroke and heart attack and all that stuff.
Probably so. Now, few words about the age-related changes. The skeleton, initial skeleton, is hyaline cartilage. Okay? Now, ossification starts at about 2 weeks. 8 weeks, 2 months. And ossification centers formed in many bones by about 3 months post-conception. Okay, long bones, like large bones, at birth are ossified, but many bones, like those flat bones of the cranium, are not ossified yet. Okay, that's why, for instance, physicians recommend to rotate the baby when baby's in the crib, so there's no malformations of the head. You know, the head is normally shaped. At age 25, practically all bones are ossified. I mentioned that there are some, like the xiphoid process here, which will not get ossified till age of approximately 40. In the young people, children and young adults, the bone formation outpaces the resorption. That's why they grow. We grow. Okay, we still grow, but, well, I'm not. Later, at about age of 38, 39, 35, bone mass and mineralization start to decrease. Therefore, healing ability starts to decrease. Okay? The density of the bone, of course, is largely determined by genetics. It harkens back to the idea that the shape of the bones depends on our parents. I mean, if you are lanky cross-country runner, you will never become a heavy lifter with gigantic arms. It's just not possible, and vice versa. Okay? That makes sense? Generally, males have just higher bone mass, because generally males are just bigger body-wise. Other treatments that can stimulate osteoporosis are electrical treatments, and it makes sense because as we talked about the response of the bone to the mechanical stimulus, we mentioned electrical signals probably participate in the bone growth. So in this case, electrical stimulation will increase the bone growth, will stimulate the bone deposition. Ultrasound, it's kind of mechanical stimulation. Okay? Daily you expose bones to the ultrasound because not everybody will be able to do the weight-bearing exercises.